very much for thank you very much for coming in this last session and the plenary session of our conference. This session or this plenary talk will be given by Professor Jon Lee. Jon Lee is a professor at University of Michigan, and let me give, it's really a very great pleasure to introduce him for this talk. John, let me give a small bio, very small bio in the website, but let me give some details. John got his PhD from Cornell University, and after that he had positions in Yale University, University of Kentucky, IBM Research Center in New York, and New York University. All this before joining the University of Michigan. John is really a very big specialist in combinatoric optimization, in polyhedral combinatorics, in nonlinear programming, in many fields of mathematical programming. John is author and co-author of more than 150 papers, and most of them are in the most prestigious journals of our field. And Johnny is also author of 4 books, 4 or 5 books, and the last one is about the maximum entropy sampling, which is the subject of his talk today. Okay, John also was the founder and the managing editor of the journal Discrete Optimization. You know it, maybe it's a very prestigious journal, and he's currently editor of mathematical programming, editor-in-chief of Mathematical Programming A. John is an Informs Fellow, and he has received the Informs Computing Society Prize. So, John, thank you very much. Really, on behalf of all the group, the organizing committee, the co-chairs, and the program committee, I would like to thank you very much to have accepted our invitation to give this plenary talk in this edition, ISCO edition. So John is going to talk about recent algorithms advances for maximum entropy sampling. Thank you, John. Go ahead, John. Thank you.
Thank you, Rita. I guess I have to share again. I lost the control though somehow when you shared. Ah, here, wait, I know where it is. Yeah, and then Ivana will tell me to go on full screen, which I will in a moment. There. Let me just clean things up here so I can see my full screen. So that picture of me, Rita, I'm sure you well know, was taken at a previous ISCO trip in Tunisia.
In Tunisia, yeah. When you are in the camel, I realized that I said that this photo should be in the desert, Tunisia desert.
Exactly. I think it should actually be the
2010.
Yeah, it could be the official logo for ISCO, even just an idea. Anyway, let me just say ISCO is always fun. I'm thrilled that you've been organizing it, and Ivana, and it's really been great to be involved. I'm looking at, I can't see the faces, but I look at all the attendees and I see, you know, half of them I count as very good friends and collaborators. So this is a fun experience for me. So let me get started. So as Rita said, I'm going to talk about this problem, the maximum entropy sampling problem. And in a way, you'll see, yeah, this is kind of an advertisement for a new book on the topic with Marcia Fampa. So let me get started before the time all disappears.
John, for some reason, we don't see the slides properly. We don't see it full screen.
You don't see it full screen. That's interesting. Do you see it at all?
We see it, but then it's too big somehow.
What about now? Is it changed?
Still not really better. It's smaller, but yeah, no.
Well, let me see if I make it, maybe I changed the local aspect ratio. Is that better?
Change.
Is that any different?
Now we see like Adobe Reader.
Let me try to reshare it. Maybe if I stop it and start again. I lost the control though.
And if you just press Control L, what happens?
Yeah, then it seemed like it was worse, but that's how I first got it full screen. Is that bad or good? Better.
Actually, I can see the full screen. Yeah.
Oh, okay. Then it's probably just me. Okay, sorry.
Okay.
If someone else can confirm, Ishwan, can you see the full screen?
Yeah, we can see the full screen. Yeah.
So Ivano, I'll have to give you a private talk at some point in the future. Okay, so I'm gonna start, but if many people can't see it, let me know through the chat maybe, and I will, well, we go out for a beer instead. Yeah, so I'm gonna talk about this problem, the maximum entropy sampling problem. So let me briefly say what it is. You have n random variables, y1 through yn, and they have a continuous density function. So you could think, if you want, like a joint normal distribution. And we're given a number s, which is smaller than n. And what we want to do is just pick a subset of those random variables of size little s. And what we want, loosely speaking, is that if we observe the random variables indexed by this set S that we've selected, we want to maximize the information obtained about the entire vector of random variables. So this really only, makes some intuitive sense if these random variables are correlated with one another. And we somehow want to pick random variables that have a lot of variability, but that also predict well the other random variables. So who knows how to do that? It's a modeling exercise, and this was carried out by Claude Shannon. And it's called differential entropy. So let me just say what the definition of it is. The entropy of the set S, which are the random variables that you're going to observe, is the negative of the expected value of the log of the density function evaluated on those random variables. I don't want to get into a full story about why that's the right measure. But loosely speaking, this will pick random variables with high variance that are correlated with the other random variables. So Shannon devised this in 1948 in his foundational paper about information theory. What you might know from that paper is Shannon's discrete entropy, and that's the more famous one. But in that same paper, he defined this differential entropy. By the way, this is Shannon here, wearing a mask because he's a very responsible person. He was an undergraduate at the University of Michigan, and he got 2 undergraduate degrees. And apparently, if you get 2 undergraduate degrees, they erect a statue in your honor. So come visit Michigan and you can stand by the statue and take a selfie. By the time you get here, probably Shannon is not wearing a mask. But anyway, so entropy has very nice mathematical properties, and it has this nice modeling property of capturing information. And I'll give you an example of where this can come from in a bit. But you can do some very simple calculations in multivariate calculus because you're calculating that expected value, so you have to integrate. And what you'll find is that if you take a affine transformation of the random variables, that the entropy just shifts by the log of the determinant of the matrix of the linear transformation. And what that means is that like ratios of entropies are not meaningful. Differences of entropies are meaningful because those differences are invariant under this kind of affine transformation. In particular, scaling the random variables this is invariant, the ordering and the difference between entropies. So that's really why it's called differential entropy, because it's the differences that are meaningful. Now, in many situations, the random variables that you're interested in have a joint normal distribution, or you can persuade them to be joint normal by some kind of a transformation. And in that case, the entropy has a really simple form. It's just the log of the determinant of the principal submatrix indexed by the set S, up to some constants. But those constants don't only depend on the number little s, which is the cardinality of the set big S that you're picking. So now you can forget about random variables and just think, I have a covariance matrix. And if I want to calculate the entropy of a set S, I look at the principal submatrix of that covariance matrix. I calculate log determinant, and up to constants, that's the entropy. So now we get to what's the so-called constrained maximum entropy sampling problem. And it's simply to pick a maximum entropy subset of size little s, but then we allow side constraints. So side constraints allow us to have budget decisions. We might have, it might be that each random variable is a cost of observing it, and there might be a budget on the total amount you can spend on observing random variables, very common in like biomedical trials. Or you might have, because we have 0, 1 variables, you might have any kind of constraint that we think of in combinatorial optimization. Pick no more than k from this set of L random variables. If I pick one from this set, I need to pick one from that set, all of the usual kind of combinatorial things that we like. So it's a very robust model. In fact, it generalizes integer linear programming, because if C was a diagonal matrix, then the log of the determinant would just be the sum of the logs of the objective function coefficients down the diagonal. It'd be an integer linear program. So this term maximum entropy sampling comes from the experimental design literature, which is a subset of the statistics literature. And this has been robustly studied in the field of statistics for 35 years or so, or longer, really. But the name actually came from that literature in 1987. I got involved in this in 1991. So 3 decades ago, I got involved in this for the first time. I heard about the problem. And for me, it sounded like a really interesting problem, not because of the application, which I'll get into more in a second, but it just seemed like a really unusual combinatorial optimization problem. At that time, I was really involved in polyhedral combinatorics, things like that. This seemed really interesting to me, that you could have this kind of strange nonlinear objective function. And so, and I was, in the enviable position of noticing that the competitors in statistics were doing the most naive things possible. They were doing greedy algorithms and simple local interchange heuristics. So this is always nice for us when we find an interesting problem and nobody has really looked at it from our point of view, and we think we can do something about it. So I started getting involved in this, 30 years ago, and I've paused, but I've never completely stopped. So it's sort of like a kind of like a skin disease that keeps coming back. If you're interested, the applications that I've been involved in, where I heard about this originally, are in environmental monitoring. I'll explain what that is in a second. But there's a big literature on this, and if you're interested, you can get the slide deck later, and I have all the references in the back. In particular, in this field, there's statistical packages, and I wrote one with a student, meaning the student wrote it, called the last one, MESGEN Cove. And what it does is it takes raw time series data from actual environmental observations and turns it into a covariance matrix. And if you think that's easy, like, oh, you just do the usual thing of averaging the numbers and looking at the pairwise covariances and loading up the covariance matrix, I mean, you're sadly mistaken. There's a lot of work to do so that you can finally believe that the covariance matrix is the covariance matrix for a joint normal distribution. If you don't care about the joint normal part, then it's very easy to prepare a covariance matrix. But if you care about the joint normal part, then you need to take special care, and that's what this package does. It's, you know, that determinant, log determinant of that principal submatrix is only the entropy if it's a joint normal distribution. So it's important that from modeling perspective, that you really take good care in how you prepare the data. But anyway, you know, modulo that, what you have is monitoring stations, and you think of time series. So it's spatially dispersed points. You're calculating observations over time. You have discrete time points, maybe weekly time points. And if you want to think about the maximum entropy sampling problem, you think of it as network contraction, where I've got n environmental monitoring stations, and I want to pick S of them to take future observations at, because it's very costly to take observations continuously into the future at all n. So we look at a subset, and we try to find the most informative subset, and that's where we continue to take our observations. So I've always used as a source of data for this to really test algorithms what's called the National Acidic Deposition Program National Trends Network. And they've maintained monitoring stations back to 1978. Stations come and go, but there's currently about 255 that are in North America, or mostly in the US. What do they measure? Well, what we're mainly interested in is the pH of wet deposition. Wet deposition means rainwater, sulfates and nitrates, and there's other things as well. But the reason is that when there's a high presence of sulfates and nitrates, that means there's a high presence of sulfuric acid and nitric acid. And those acids, what they do is they increase the pH of precipitation from its usual value. So the kind of nominal value is not 7, which you learn in class is neutral, but real rain that's not is always a little bit acidic. It's like 5.6 or so. And a pH of less than 4 is considered acid rain. And, you know, 4 doesn't sound like much smaller than 5.6, but this is a logarithmic scale. And so 4 is very acidic. And why do we care about that? Well, it has a bad impact on all kinds of life and on infrastructure. So things deteriorate faster, and you really don't want this. This is how rainwater is collected in this network. You think this is, you could decide this is a very sophisticated device or a very basic device. It's a 5-gallon bucket. And well, there's 2 of them on this table, but there's a lid on the bucket, and the lid opens up when it's raining and closes when it's not raining. Now you think, well, don't you usually do the opposite in life? Well, usually in the opposite, you're trying to shield yourself from rainwater. This, you want to collect the rainwater. Well, you think, why close it at all? Well, if you leave it open, then you collect more than rainwater. You collect what birds drop. And that's a whole nother kind of thing to, if you're trying to track avian flu, maybe that's what you do. But for rainwater, you want this very sophisticated bucket that doesn't cost 5 euros. It costs, you know, more like 10,000 euros. So that's what these things look like. This is, you know, what you learn in science class, a little cartoon of how these acids are formed and how these ions that I mentioned that you can measure come about, but we'll skip that. If you're a little curious how things are going, this was 1987, and you see it's not a political map. It's a, you know, maybe there's some similarity, but it's the black dots are the monitoring stations. You see they're quite spread out. And the high levels of acid rain are concentrated in more industrialized areas. Well, that was 1987. Since then, there's been in the US something called the Clean Air Act. It's been revised many times, and it requires monitoring and you know, mitigation. And there's been tougher standards on automobiles, on manufacturing plants. And so as a result, here we are in 2018, not that long ago, although 2018 seems like the infinite past after what's happened a few years. But you see things are actually a lot better. And I think, the lesson of all this is that things can get better if people are watching. Yeah, one more thing before I get into the mathematics and algorithmics. This is the log of, you take logs because of heavy tails. This is the log of the sulfate concentrations at a particular monitoring station in Ohio. And this is over months. And what you see is a 12-month periodicity. And so these are things you have to deal with the raw data. You have to take out this periodicity so that ultimately what you see looks like, multivariate Gaussian noise. So a lot of work of data processing before you get into the optimization, but we'll assume that's all done and you have a nice covariance matrix. Even once you've, surmounted all that difficulty, you have this covariance matrix. Now you start to think the way we think as combinatorial optimizers. The maximum entropy sampling problem, even without the side constraints. So you just want to pick S out of N things as your only constraint. That's a NP-hard problem, and is a very clean reduction of the stable set problem in a graph. So if I have a graph and I want to know, is there a stable set of size S vertices? All you do is you take the adjacency matrix of the graph and you put N down the diagonal, and maximizing the entropy, finding a biggest log determinant submatrix of size S solves the problem. So if that determinant is N to the power S, then the submatrix has to correspond to a stable set of size S. And it's just kind of a matrix algebra proof to see that that's the case. So that's the hard side that justifies, all the nasty stuff we do, cutting, everything we do in combinatorial optimization. Once we find the problem is NP-hard, it gives us license to do all kinds of things on the borderline of engineering and mathematics and algorithmics. So it's also nice to look on the easy side. And if the C matrix or its inverse is tridiagonal, so that just means numbers on the diagonal, numbers on the two echelons that border the diagonal, and zeros everywhere else, then you can solve the problem by dynamic programming. And you can generalize this to when the support graph, so tridiagonal means the support graph of C is a path. And if the support graph of C is actually a spider with a bounded number of legs, then, well, you might scream because it's a spider with a bounded number of legs. Even a few legs is scary, but you can still solve it by dynamic programming. So then you can move in other directions and think about what are nice properties of this function log det of a principal submatrix. You can think of this as a function on S, and it's a submodular function. And this is known for a long time in matrix algebra. This is known as the Hadamard-Fisher inequalities. In combinatorial optimization, it was known at least since the 80s. Probably before that. So last little general thing before we get into algorithmics is some properties of this of the optimal value. So Z of CSAB is the optimal value of this constrained maximum entropy sampling problem. The first thing is it behaves pretty nicely under scaling the matrix. So if I take the covariance matrix and scale it by gamma, then the optimal value just shifts by S log gamma. It's very easy to check that that's the case. That's useful, surprisingly useful. So if I have a bounding method, right, we're going to do branch and bound actually. And so I'm going to look for upper bounds on this maximum. If I have a bounding method and I apply it to the unscaled problem, the problem on the left, the Z of CSAB, I could as well apply that bounding method to the scaled problem. And you might think of applying a reasonable bounding method to the scaled problem and then subtracting S log gamma will be the same as applying that bounding method to the problem on the left. And no, that's not the case for many bounding methods. So that's good because it means that we can try to find the best scaling to minimize what you see on the right and get the best bound possible of this form for the problem on the left. the same kind of principle applies to what we call the complementary problem. So turns out that if you have this maximum entropy sampling problem and you take the inverse of the covariance matrix and then try to select n minus s points instead of s and appropriately change the constraints, then the value is exactly the same as the original problem up to this shift of log determinant of the original covariance matrix. Same idea, if I have an upper bounding method and I'm trying to get an upper bound on this problem on the left, I could instead apply it to this problem on the right, shift it by log det c, and get a upper bound for the problem on the left, and no, it's not always the same upper bound that you'll get. So again, you can get, for any bounding method, you can potentially get 2 upper bounds for the problem on the left. And then finally, there's another method we call masking. We called it this before the last few years. What you do is you take a correlation matrix. So that's a covariance matrix with ones on the diagonal. And then you take its element by element product with the covariance matrix. And what you do when you do that is you create disorder, or you add information. So in other words, the entropy can only go up when you do that for every subset of every feasible subset. And so you think, well, that's a bad idea. Why would like in combinatorial optimization, it'd be like taking a problem and loosening the constraints. And but here it can benefit you. So again, if you have a bounding method and you would apply it to the problem on the right, even though the optimal value went up, the upper bound on that might go down. And so that's another generally useful technique. So armed with these 3 techniques, we want to soon get into the actual bounding methods. Maybe before I mention that, let me just say quickly, there are, we're going to be doing branch and bound, so you do need lower bounding methods too, and so you can use all these classical techniques of greedy and local search, and greedy from the top down by doing greedy deletion, and everything you can think of. There are also approximation algorithms, sort of, for this problem. And the idea is that this problem is a submodular maximization problem. And for non-negative submodular maximization problems, there are constant factor approximation schemes. Now, our entropy is not non-negative generally. So the differences of entropy, we talked about that, but you can make the entropy very negative. It's the actual value of it doesn't have any meaning. It's differences that matter. And so you could assume like that the minimum eigenvalue of the covariance matrix is somewhat large, so that all of the entropy values are non-negative, and then these kind of submodular maximization results would directly apply. We don't take that view. We take the view that, many of us have been playing with since Martin Gretschel started, really decimating some problems like max cut and linear ordering and like this in the 80s. We take the idea we're going to try to solve problems exactly and see if we can solve bigger problems than we could by enumeration, and see, how large we can go. And you see, for traveling salesmen, people, well, at least one person can go very large these days. But that's our goal, is to basically do branch and bound, come up with good bounding methods, do every trick we know about from branch and bound, reduce cost fixing all these tricks, and try to solve big problems to exact optimality, or at least get small gaps. One little comment before I get into these upper bounding methods is that there's something called Gibbs inequality, and it basically tells you that the Gaussian has the maximum entropy among all random vectors with the same covariance matrix. So, we restricted our attention to Gaussians at the beginning, but if I give you the covariance matrix and I say maybe it's not Gaussian, if I calculate the entropy as if it's Gaussian, do I do the log determinant and then add those constant factors? That's an upper bound on the entropy for any distribution. So what that means is that if you want to do branch and bound and you don't have the Gaussian assumption in play, you can still use the upper bounds that I'm going to talk about for the Gaussian, and they still apply for any distribution whatsoever. So how do we do branch and bound? For this audience, you all know what branch and bound is. Let me just kind of say it in a clear way, because there's some little wrinkles here. So, branch and bound maintains a list of subproblems. Initially, our subproblem is the original problem. And what do we need? All we really need is a bounding method, a branching rule, and then we need lower bounds. We need feasible solutions, because that's what lets us throw away subproblems. You have to be able to branch, and then you need the bounding method to be consistent with the branching rule, so you can calculate the bounds on subproblems. Here it's quite easy. When you fix things out of the solutions, that's what I call F0, the indices that are fixed out of the solution, and F1 is the indices fixed into the solution. Into the solution, you calculate the entropy of that set, log det of that principal submatrix. Then what you do is you condition. So you look at the conditional covariance matrix, conditioning on the things you're observing or fixing into the solution. All that is a short complement in the covariance matrix. And then, well, I already picked cardinality F1 elements, so now I only need to pick S minus cardinality F1. So really, the point is that when I branch, there's a constant I have to add to the value based on the fixed variables. And then my subproblem is again of the form that we've been talking about. It's just a different covariance matrix as a conditional covariance matrix. So yeah, initially I have the original problem is my only problem on the list, and I have a lower bound any heuristic solution. To say this carefully, I need to talk about the continuous relaxation of a subproblem, and that's what I have here. So I fix variables to 0 if they're in F0, I fix them to 1 if they're in F1, otherwise I have all the constraints. And I don't assume that the unfixed variables are discrete at this point. So this is the feasible region of the continuous relaxation of a subproblem. And then what do? Well, the way branch and bound works is it maintains some invariant property, and it processes problems on the list of subproblems. And it does this in some way so that at the end, based on the invariant properties, you can conclude that you've solved the problem. So what are the properties? What we want is that every subproblem on the list is feasible, but the continuous relaxation of the subproblem does not have a unique feasible solution. If it did, I would take that unique feasible solution, see if it was integer. If it was integer, I would calculate its objective value and update my lower bound. So I don't put a problem on the list if its continuous relaxation has not a unique solution. And then the other property, I want to make sure I have enough problems on the list. So I just make sure that if there's a feasible solution of the problem that I'm given, and its objective value is better than the best solution I know, better than the lower bound, then I make sure that there's some problem on the list that this solution is feasible for. And then I haven't lost any improving solution. So with these properties, it's clear you can stop when the list is empty, because if you had these properties and the list was empty, then in fact the lower bound would have to be the optimal value. So that's how I teach branch and bound. So how do we process problems on the list? We pop problems off the list, and we we calculate the bound. If the bound says we can discard it, we discard it. Otherwise, we choose a branching index. And how do we branch? We take this index J that hasn't been fixed, and we either fix it into the solution with the other variables that are fixed in, or we fix it out of the solution. So we have these in children and out children. And it's clear that every feasible solution for a parent is feasible for one of his or her children, which I don't know if that's always true in life, but anyway, how do we treat our children? Now, the point is no child is a bad child, but our goal in life is to discard our children so we can get our lives back as we knew them before we had children. So that's what we do. I won't go into the details of it. I think you know mostly how it goes. We check for if we fix a variable into the solution, if it's the unique solution satisfying the cardinality constraint, we just see if it's feasible to the side constraints and maybe update the lower bound. We proceed similarly if we fix something out. The only other little wrinkle is if we can't discard a solution based on that, we look at the feasible region of the continuous relaxation and we check, solving a single linear program, whether there's a unique solution to that continuous relaxation. And as I said before, if there is, we just check if it's binary, and if it's binary, we potentially update the lower bound. And if it's not binary and it's a unique solution, then we can discard that problem. So that's how branch and bound works. Now we really get to these bounding methods. So the very first bounding method is if I'm trying to bound the determinant of a principal submatrix of size S, I can just take the eigenvalues, the S biggest eigenvalues of the whole matrix, multiply them together. And because of what's called eigenvalue interlacing inequalities, I get an upper bound this way. You can apply that masking idea where you take the covariance matrix and you first pre-multiply it element-wise by a correlation matrix like the identity matrix, and then you get another simple upper bound, which just says take the product of the S largest diagonal entries of C, which is the S largest variances of these random variables, and log them and add them up, or take the product and take the log of the product, and that's also an upper bound. I won't get into more of these upper bounds, but there's a big literature on this, what I call these spectral bounds and masked spectral bounds and extensions of what I just talked about to side constraints. That what I just said only works for when there's no side constraints. But if there's side constraints, you can apply Lagrangian relaxation. If you want to think of more general masks than the identity mask, there are these papers that I did with Kurt and with Sam Burer on finding good masks. You can look at combinatorial masks. So that's picking correlation matrices that are blocks of ones down the diagonal. And then you get into kind of interesting combinatorial problems, and finding good masks can mean solving matching problems or integer linear programs. And well, there's one more thing, I don't want to talk about it now. One more idea that's very general is the idea of using convex programming relaxations instead of these spectral bounds. Nice thing about convex programming relaxations is including the side constraints has no conceptual difficulty at all. If I have a convex relaxation of the problem without side constraints, I just throw in the side constraints, ax less than or equal to b, and I still have a convex program. The other nice thing, probably a nicer thing even, is there's a variable fixing methodology which works for any convex integer nonlinear program based on duality of the convex relaxation, Lagrangian duality, and you can apply it directly almost without thinking. If you explicitly have upper and lower bound constraints, 0 and 1 constraints. So just like you do reduced cost fixing in linear programming, if you have, say variables that should be 0 or 1, you look at the relaxation and you look at variables that have very big reduced costs, and that means you can fix the variable at 0, 1. Similar methodology works here, but you need to have those constraints explicit. And I'll show you in a quick example soon of a case where they're not so explicit. But anyway, when you have that, you can do this kind of variable fixing in a very standard way. I could fix variables at 0, 1 if some dual variables associated with these constraints are large enough. So here, these are the dual variables for these constraints. And if they're large enough, meaning looking at the difference of it's looking at the objective gap compared to the dual variables, then you can fix. So I won't say more about that, but that's a very useful technique overall. So now let's get into some of these bounding methods. So a little warm up is a little calculation here. If I have the characteristic vector of a set S, so the 0, 1 vector associated with choosing the set S, if I look at this form, so it's diag matrix with the zeros and ones down the diagonal, C, the data matrix, and then again diag X, and now this is the diagonal matrix that's the complement of the characteristic vector of x. If I work all that out, what I get is this. And well, that's nice. Now, if I take log determinant of this, I get what I want. I get log det of CSS. And now you see why this part's important, because that's how I got the identity here. If I had zeros there and I tried to do log determinant, I would get determinant is 0, and then I would get log determinant is minus infinity. So I really need to do this complementing here to get the correct objective when I take log det of this. So what it does, that leads you to this kind of relaxation. Just taking this objective function that we just talked about, doing log det of this matrix and putting the constraints back. So that's a formulation as an integer nonlinear program. The problem is the objective function is not a concave function, and because we're maximizing, we want a concave function on the continuous space. So that's a problem, and that's what, oops, went the wrong way. That's what we looked at back a long time ago, that you can take that exact function I had before and play with the x in a certain way. So instead of having just x here, we have each xi to a power pi over 2. And here, instead of having, we had identity minus the characteristic vector of x, we can have some other numbers, some diagonal numbers, di, and these powers. And so by choosing this, these pi's and di's appropriately, we can curve this function that I showed you on the previous page to make it concave. So once we make it concave, then we get a real convex programming relaxation, and we can solve this somehow with a nonlinear programming algorithm to global optimality. And that's what you need to be able to do if you're going to do kind of convex integer programming, branch and bound for a nonlinear problem. You can also use this complementing and scaling idea to get better bounds. In fact, this was the paper where we developed these ideas. A totally different bound that's actually quite recent is by Cardan Stryker. It's called he calls it the links bound. We call it that too, but he came up with the name. It's log det of something that's linear in x, and so that's why it's links. And here's what it looks like. There's a half here. You'll see why in a second. Log det of some matrix L of x, and then the same constraint. So here comes L of x. It looks sort of similar to the first thing I wrote, but what's interesting is that the C appears twice and the diag x is in between them. But what I wrote before was the diag x was on the outside and the C was in between. Because C occurs twice and you're taking determinant and logging it, the power of 2, it's like C squared. That when you do that, that's why you need this half here. So this actually, I'll show you why it's a relaxation. It's not so obvious in a second. There's a kind of a very clever idea of Kurt's, but it's a really nice formulation. It's convex. I mean, there's a convex program, so we're maximizing. The objective is concave. It's smooth. It's efficiently solvable with nonlinear programming software. You can use specialized software like conic software like SDPT3, or maybe I'm not sure Mosaic will work on this one. But you can also use general purpose nonlinear programming software like Nitro, and that's what we did with Zhangzhu Chen. This is self-complementary. That was a nice nice property of this bound. So if I look at the complementary problem and calculate the same bound, I get the same value, which is a property of a spectral bound, but it's not a property of that previous bound I showed you, this nonlinear programming bound. The bound is very sensitive to the scale factor that you might put in front of this this term here. And finding the optimal scale factor we were able to show is a univariate convex minimization problem. So you can actually find the best scale factor for this bound. So it really has some very nice mathematical properties. Why it's a bound, again, I don't have that much time, I won't go through all the details, but if you work out like what this is, when you plug in the characteristic vector of a set S, you get this. And well, here's the important calculation down here. If you calculate log det of this, so that's what I'm doing here, log det of that mess, and work out and use short complements, what you finally get is exactly this. So that's why you need the half, and then you get log det of CSS. And it's just a couple of lines proof, as you see, but it's kind of a very amazing insight of Kurt's after working on this problem for 25 years, that he came up with this this very clever relaxation. Yeah, you can mask and scale this bound, this links bound. So here again, masking means taking the covariance matrix that occurs twice here and multiplying it element-wise by a correlation matrix. And then you can put a scale factor in front and possibly improve the bound by choosing M and gamma appropriately. What we were able to show is that you can get a big improvement this way. So we found a sequence of positive semi-definite matrices, CN, so that if you don't mask, so that means taking the mask equal to the all ones matrix versus masking with the identity matrix, so two very simple, really no mask or very simple mask. And then you look at the optimal scale factors for both of these. What you can do is make the difference of them grow as a linear function in N. And that's a big gap to get linear growth in N for an entropy bound. So what it means is that masking can really help the links bound quite a lot in the best case. So these are tailored problems to show that you can really get a big improvement by masking. And we're working on mask optimization to really see for typical problems if we can get this kind of improvement for the links bound. There's another great bound called we call it the factorization bound of Nikolov. And it's been worked on more recently by Lee and Shi. We have some really nice results concerning this bound, and we've worked on it ourselves. The bound is just this. It's the sum of the logs of the S largest eigenvalues of this. And what this is doing is it's combining Kurt's idea with our earlier spectral idea. So you see eigenvalues, but not of the principal submatrix. But then you see Kurt's idea of putting the X between two factors, but it's not the actual matrix. So you split the matrix, you factor it into F and F transpose. And then once you've split it, now you do a Kurt's idea, not for C on both sides, but for F transpose and F on both sides. It was really a very clever idea. And well, it's not a convex program. And so it looks like trouble. But what you can do is really a very clever idea is you can take it to Lagrangian dual. And the Lagrangian dual is always a convex program. So again, what I wrote here, actually, this isn't quite right. The Z fact should be, well, it depends. The problem is really this with discrete variables. But when I take the Lagrangian dual, I want to make this continuous. And now I write down Lagrangian dual of the continuous relaxation. And the Lagrangian dual is always a convex program. Now, it's a bit of a nasty problem, where to go here, because you see there's a matrix variable, a positive semi-definite matrix variable, and the size of it corresponds to the number of columns of F. Now, the number of rows of F is always N. Number of columns for a full rank C will be equal to N, but for a lower rank C might be somewhat smaller. But for a full rank C, this is a big matrix variable. And so this is kind of a nasty problem. You have semi-definiteness constraints, and you have the constraints here are linear, but you have this PSD constraint on the matrix variable. And then you've got this objective that has, eigenvalues in here. So it's not such a well-behaved problem, and it's a convex program, but it's not so easy to solve. But the really clever idea of Nikolov is take the dual again. And when you take that Lagrangian dual twice, you think you take the dual, you end up where you started. That's not true if the original problem wasn't convex. So if you take the dual twice, you get a nice convex program now after some work, which is back in the space of only N variables, and all the difficulty is hidden in this gamma function here. So before I briefly tell you what the gamma function is. This is a really nice problem. It's convex, it's reasonably smooth. It's efficiently solvable with general purpose nonlinear programming solver. That's what we did with Chen. And it's independent of how you do that matrix factorization. So you could do Cholesky, you could do spectral decomposition, you could take the matrix square root, lots of possibilities, it doesn't matter. It's invariant under scaling, so there's no issue of finding the optimal scale factor. You can prove that this dominates the spectral bound pretty easily. So if you're willing to pay the cost of solving this problem, even though the spectral bound you can solve very quickly, it's you can't do better with the spectral bound. And but with all these nice properties, there's one property that it doesn't have. It's not invariant under complementation the way Kurt's Links bound was. Oh, I missed an either. Anyway, so you can get two bounds for the price of one because of this. The gamma function, I don't have time, is you can look at the slides later, but this is the definition of it. It's got a sort of an obscure definition, but it's a function, a certain function of the eigenvalues of the matrix. So that's really the thing to keep in mind. This is some function of the eigenvalues of this matrix, so it's not a trivial problem to deal with. But you can write down the things Nitro would need to solve this relaxation. So you can write down under some technical conditions the gradient and the can you write the Hessian of this? No, just the gradient of this. Well, maybe you can actually write the Hessian under some technical conditions. Let's see. One more bound is the BQP bound. This is kind of a curious thing. So Kurt worked on this fairly recently, but Christoph Helmberg told us about this idea back in 1995, told me and told Kurt. And we said, yeah, that's really kind of a cool idea. But part of the reason we didn't work on it is there really wasn't software around that could handle this. So you had a log det objective, so not a linear objective, and you had semi-definiteness constraints. So there was some SDP software kicking around them, but really handling this problem wasn't so easy. And so, well, Kurt and I, we got on with our lives and sort of forgot about this. And then somehow Kurt remembered and told me about this idea, and I said, yeah, I think Christoph told us about this a long time ago. And I found like these two pieces of paper where I had proof of this, because my memory can be a little shaky. But anyway, it's the standard thing. You take little x, your vector of decision variables, you lift it to matrix space by defining a new matrix X, which is meant to be XX transpose, a rank 1 matrix. But you can't really enforce this. It's a non-convex constraint. So you do the Shor relaxation of it. You write this down. And this is a standard way to relax that kind of constraint in quadratic 0-1 optimization. And well, you want to keep the association between the diagonal of XX transpose and big X. So you put this constraint, and then you can also see that you can write down some other simple constraints. And so now you need what the objective function looks like. It's not hard to check that this is the right objective function using similar reasoning as before, that the matrix X now really easily picks out the right principal submatrix, but you still have to correct the part you haven't picked. So this is nice. You can use software like SDPT3 to solve problems like this. So SDPT3 is particularly nice among semi-definite programming solvers for dealing with this log det objective. And well, same thing, the bound is sensitive to a scaling parameter, but turns out we could show that it's actually convex in a scale parameter, so you can find the optimal one. And variable fixing is not so easy here, because you see in this formulation, we don't explicitly have the constraint that X is between 0 and 1, little x is between 0 and 1, these constraints, but it's implicit in the Shor relaxation constraints and this other constraint here. And so you've got to figure out a way to take dual variables here and take information from them and get things that behave like dual variables for these non-explicit constraints. But if you do that, you can do variable fixing as well. And that was another clever idea of Kurt's in this paper of his on the BQP bound. So lastly, we have a way to mix bounds. You can look at a whole bunch of bounds. Say, we already seen a bunch of bounds. If I have m different bounds, I can get their values. So that's what's meant by VI, and then I mix them. So what I do is I define V of alpha. Alpha is a weighting factor on each bound. And I choose some alphas that are non-negative and add up to 1. And I take a weighted combination of these bounds. Now you think, well, how could that be a good idea? If I have one bound here and one bound here, and I took a half of each, aren't I going to get something in between? But the point is that you're not taking just a weighted combination of these values of the bounds. You're solving another optimization problem where the variables are shared between all the bounds. And so if you have a bound here and a bound here, and if you think about what this function looks like as a function of alpha, it's going to be convex in alpha. And so you can actually get a lower bound than the two bounds that you mix. And that idea really works. And you can get lots of different bounds from these other bounds. So you get this, as I said, convexity in this weighting vector. We have an algorithmic framework to choose the best weights. We have a variable fixing methodology, and this is where I didn't get into it, but we assume a certain form of these bounds here, that it's a function of a linear function in the decision variables like the links bound, but also other bounds have this property like this DD fact bound and the complementary DD fact bound. So lots of bounds can be put in this exact framework that I've described here. And when it's in that framework, then we have this fixing methodology. And you can also mix like the Boolean quadric bound and that bound applied to its complementary problem. If you do that, you can add cutting planes to make these bounds even stronger. So you can put triangle inequalities. Once you have, like max cut, once you go into the space of the edges, you can put triangle inequalities. There are even other inequalities that are specific to BQP and its complement that work out. Where are the computational results? These should be coming now, right? Well, they're in the papers. So read the papers if you want to see the computational results. I never like to see computational results in real time because people put these graphs and then they never tell me what the vertical axis is. And I'm staring at these things and I see one curve is higher than the other. And I feel, and even if the axis is labeled, it's too small for me to see. So anyway, look in the papers. That was a pretty good cop out, I think. And where can you read more? In our book. So, as again, the book is our child, and no child is a bad child. So go look at the book. And I am done if anybody is still there. I couldn't see anybody because I was full screen. Rita, you're okay. Now you're unmuted.
Thank you very much, John. Thank you very much for this really very nice and rich talk and very interesting talk. So now we go for the questions. Okay, we have time for the questions. So any questions?
I have questions. But I'm not going to tell you.
I see a question from Ivana. Factorization bounded. Is there a hierarchy of bounds?
No. So you can
is used.
So you can prove a short proof that the factorization bound is independent of how you factor. Now there might be some numerical issue about one factorization being a better factorization because it does come into the constraints, but you can actually show more than that the bounds are equivalent. The way we do the variable fixing, you need dual variables, and so even though I end up with this problem DD fact, the intermediate problem, defact, I need to calculate dual variables for. And we can even show that the dual variables that you would calculate for defact are independent of the factorization, which to me was a bit surprising, but that it comes out.
Okay. Okay. Other questions?
I have a very good question. Where's the next ISCO going to be?
Yeah, this will be just after a couple of minutes.
I'm trying to keep people around, you know?
Yeah. Okay. So,
I can ask a question.
Yeah, go ahead. Yeah.
So, I mean, some of these related problems where you have these log determinant type of objectives where these optimal design problems, right? I think Wei-Jun Shea and others had shown recently that, not recently, maybe a few years back, that some of these greedy heuristics have guarantees actually. So I was just curious, you were saying at the beginning that, statisticians use these greedy heuristics. Did you use them to at least like sort of as a good primal source of good primal solutions or something?
Yeah, I mean, so the statisticians use these mostly greedy heuristics and interchange, simple pairwise interchanging. And what we could actually verify, this was already some years ago, is that usually the solutions they got were optimal. And I think this is a function of the fact that the first algorithms to get approximation guarantees for non-negative submodular functions are in the spirit of greedy and local search, and even more sophisticated algorithms, not the most sophisticated, but more sophisticated algorithms for submodular maximization, in the case of non-negative submodular functions, are greedy and interchange. So it's not a surprise that, we could work hard and do branch and bound and solve to optimality and show that some of these solutions were really optimal that statisticians got. Now that's when you look at problems with like n equal 40 or 50. If you get to n equal a couple of hundred, no, I don't think greedy solutions end up being optimal for these.
But still, most of the work is actually proving the dual side essentially.
To proving, I mean, just like interlinear programming, you work like crazy. In fact, probably it's kind of boring to develop more and more complicated primal heuristics. But in the end, you can put in much less time to get the optimal solution than to verify that it's optimal. That's for sure. But curiously, we've got a data set. I think it was your data set for n equal 2000, this Reddit data. And this problem has, I don't know if I ever told you this. So we worked with that data set, and the rank of that matrix is not full rank. It's like 949 or something like that. Maybe you remember. But if you calculate iteratively, the links bound and the factorization bound iteratively back and forth, and in between those iterations, you fix variables. These things work together really well in a synergistic way. So the links bound can't fix anything, and it's terrible for that problem. But if I first calculate the factorization bound and then use convex duality and fix variables, then the links bound all of a sudden can fix variables for modest size s, like s equals 60. Now, 2000 choose 60 is a huge number, so it's not something you could solve by enumeration. But you can actually iteratively fix all the variables and solve this to optimality with no branching. So that's a case where the upper bound side is very tractable for this problem, at least in that example. I don't remember if you apply the primal heuristics to that same instance, whether it would actually get you the optimum.
Can I ask one more question?
Go ahead, Ivana.
John, so basically you're applying now a very sophisticated branch and bound method. What comes, of course, to my mind is because it's submodular maximization, the standard submodular cuts by Nemhauser and Woolsey, but they are probably dominated by all these other bounds. So
yeah, I mean, we don't have a theorem, but if you look like it in Nemhauser and Woolsey's book, they have a general cutting plane method for submodular functions. And I tried this, I never published anything about it because the results were, so miserable. So I tried this years and years ago and gave up on it. But Marcia gave a talk maybe yesterday, I think yesterday, and she talked about outer approximation for these problems. So it's not just using the general submodularity cuts, but cuts that are very specific to the relaxations that we're using, and those results seem promising.
You combine them, or you just derive an outer approximation-based branch and cut without this?
Yeah, right now we're just doing a standard. Well, it's not completely standard, but it's an outer approximation algorithm with no branching. But it's very interesting things that we've had to worry about using different kinds of cuts, like disjunctive cuts. That's one of my favorite topics. And so we've tried disjunctive cuts, and finding good linearization points seems to be a very difficult matter. And that's why it seems to be useful to solve many relaxations, not for the cuts that you can get for them, but for the diversity of the linearization points that you get from them.
Okay, other questions? Other questions? Okay.
I have a question. Where is the next ISCO?
Okay, thank you very much. Thank you very much.
Thank you,
John, for this nice talk.